All right, so picking where we left off, we just defined series. We talked about it converging and diverging based on its partial sums. The first thing that we want to do is we want to look at something called geometric series. Geometric series are the most common kind of series, and most importantly, it's probably the only type of series that we have, that we know exactly what happens. So a geometric series is a series that is in the form a plus ar plus ar squared plus all the way down to ar sub n minus 1. And then it just keeps going. Okay, so basically what we're doing for this infinite series is that we have some constant that's on every single term, and then to get to the next term, you're just multiplying by this value r. If we want to write this in like a sum format, we would write it like this. So you would say the infinite sum, as my index n goes from 1 to infinity, of ar to the n minus 1. All right, so I hope that you've seen this infinite sum notation before. These are saying the same thing. Okay, I do want to point out that they're not always written like this. Sometimes the index will shift. So sometimes we'll write it as the infinite series. Well, let me write it so that it's in the thing. Or the infinite series where n starts at 0 and goes to infinity. And then it would just be ar to the n. So make sure you have both of these in your head when we're talking about geometric series, because you'll see questions that look either way. Either the index starts at 1 and then it's ar to the n minus 1, or the index will start at 0 and then it's just ar to the n. But keep in mind that both of these are the exact same thing. Okay, so this is the definition for a geometric series. Let's move on to see if we can figure out when does the geometric series converge and what does it converge to. So we can determine the convergence or divergence of the geometric series. And to do that, we're just going to use a little trick. And that trick is to look at the partial sums again. So the partial sum, s sub n, remember that this is just the first n terms added together. So a sub 1, well, not a sub 1, sorry, that's just a. The first term a, the second term ar, the third term ar squared, plus all the way down to the nth term. The nth term is ar sub n minus 1. Okay, and this does not go on forever, right? Remember, the partial sums is just the first n terms added together. What we're going to do is that we're also going to look at the same equation up top there, but multiplying everything by r. This is a very common trick for these series. If I do multiply both the left-hand side and the right-hand side by r, the right-hand side is going to be ar plus ar squared plus ar cubed plus all the way down to ar sub with an exponent of n. Basically just shifting the r's all around. Next, what we're going to do is we're going to subtract the two equations. If I subtract the left-hand side, it's going to be that s sub n minus r s sub n. Oops, I put this as an exponent here. I don't know what I was thinking. That should be a subscript. Oops. Okay, so the s sub n minus, from the second equation, r s sub n. And then if I subtract the right-hand side, some pretty cool stuff's going to happen. So this a is just going to stay there because nothing will cancel out from that. But this term ar is canceled out by this term ar. The ar squared is canceled out. There's an ar cubed that cancels out. And even an ar n minus 1 cancels out with an ar n minus 1 here. The only term that's going to be left over in the bottom is that very last term, the ar to the n power. What I want to do is I want to solve this for the partial sum. So next thing, I'm going to factor out that partial sum from those two terms. And then divide by that 1 minus r. So my partial sum can be rewritten as a big fraction. I'm also going to factor out the a from that right-hand side. And we get this. Okay. So this represents the partial sum. So this is just adding up the first n terms. Let's think about, when does this partial sum converge or diverge as a sequence? The only thing we have to worry about is this one exponent of n. If this makes it blow up to infinity, then of course it diverges. If it doesn't blow up to infinity and it converges to a limit, then of course the whole sequence is going to converge. If you just think about it for a little bit, as long as the absolute value of that r is less than 1, so if this r is a fraction, then when that n goes to infinity, this term just goes to 0. So as long as the absolute value of r is less than 1, then, like I was saying, r sub n is going to go to 0, and thus that means that my partial sum s sub n is going to converge to just a over 1 minus r. And since that is what the sequence of partial sums converges to, that means that is what the infinite series converges to. Okay, so let's think about all that again and kind of rewrite it all out. For geometric series, so remember, geometric series are in this form. The infinite sum from n equals 1 to infinity of a r to the n minus 1. So it has a constant value, and then it has some ratio r raised to the n minus 1 power. This converges as long as the absolute value of r is less than 1 and converges to a over 1 minus r. If the absolute value of r is bigger than 1, then it diverges. Okay, so let's just look at a quick example or two, or three. So the example we're going to look at is the infinite sum. As n goes from 1 to infinity, of 1/9 times 1/3 to the n minus 1 power. The question is going to be, does this converge? And if so, to what? Okay, so this does converge since my r value is 1/3, and that is less than 1. Right? The a would be 1/9, my r would be 1/3. Since my r value, the ratio value, is less than 1, that means that this geometric series is going to converge. And it converges to, remember, it's a over 1 minus r, where my a is 1/9 over 1 minus my r is 1/3. Sorry, that's kind of small, but you can just plug this in the calculator at this point, or do it in your head. That's going to be 1/9 divided by 2/3, which if you do it all and simplify it down, comes out to be 1/6. So this thing, all multiplied out, and then adding all of the different terms together, that total sum adds up to be 1/6. That might be kind of hard just to see from this, so let's at least get a few of the terms written down, so maybe you can visualize it at that point. So if I expand from here, plugging n to be 1 into this, I get 1 minus 1, which is 0. 1/3 to the 0 is just 1, so I'm just going to get the 1/9 out in front. Plus, if I plug n to be 2, that's going to be 2 minus 1, which is 1. 1/3 to the 1 is 1/3 times 1/9 is 1/27. And then there's just a pattern to it. Every single time we're just multiplying by a 1/3. So the next one's going to be 1 over 81 plus whatever 1 over 81 is times 1/3, and so on and so forth. So if I take this infinite sequence of values that are all added together as a series, those all add up to be 1/6. Okay, so I have some more examples because these do get a little bit more difficult. So let's look at the next one. Let's look at the infinite series n equals 0 to infinity of -1 to the n 5 over 4 to the n. Okay. A lot of times when you're given these series, they're not going to be written in that perfect format for the geometric series, the a times r to the n or n minus 1 power. So you may have to use some tricks here. And you have two different ways of doing this. One way of doing this would just be to write out the first few terms, because then it's easy to see what the a and the r are going to be. So let's just do that first. If I plug n to be 0 into this, then anything that's raised to the 0 power is just 1, and I'm just going to get a 5. If I plug n to be 1 into this, I'm going to get a negative 1 times 5 is negative 5 over 4, so minus 5/4. If I plug a 2 into it, just to make things a little bit quicker, I get 5/16. If I plug a 3 into it, I get 5 over 64, and then it just keeps going forever and ever and ever. So this is one that we haven't seen yet, but this is pretty common as well. This is called an alternating series, where you have positive, negative, positive, negative. This is geometric still. The constant value that I have with all of these is going to be 5. In fact, that's always going to be the case. Whatever the number is out in front is going to be the a of the geometric series. And then every single time I'm multiplying by negative 1/4. So for this series, I have that my a, the a is 5, and my r is negative 1/4. Okay. Another way of figuring that out would be to just rewrite your infinite sum into that format that we're used to. What you can do is, since that 5 has nothing on it, I can just bring that to the front. And then I have negative 1 to the n divided by 4 to the n. Because both of these are raised to the n power, I can combine them together and then raise the whole thing to the n. Now it's in that format where my a is 5 and my r is going to be the negative 1/4. The r is allowed to be negative, as you can see. All right, that means to find the sum, remember the sum is a over 1 minus r. So for us, that's going to be 5 divided by 1 minus negative 1/4. Be careful of the double negative down there. So this is going to be 5 over 1 plus 1/4. 1 plus 1/4 is 5/4. 5 divided by 5/4 is 4. So this infinite series adds up to be 4. One thing you may want to do in your calculator is just start adding up the first, 10 or so terms. You'll start to see that if you keep adding up the terms as you go, it does eventually get closer and closer and closer to 4. Okay, so I do have some other oddball examples of this, but I think I'm just going to let you guys work on those oddball examples on your own on the homeworks. So I'm going to kind of skip ahead a little bit. Good. Yeah, so I'm pausing this video now, and let's look at the last video for section 2.